Hello everyone, I'm Ran Shu from Microsoft. Today I will talk about direct universal access, making data center resources available to FPGA. Currently, FPGA are widely deployed in major cloud service providers, including Microsoft and Amazon and so on. They are used to accelerate many applications, including computation, networking, and storage. FPGAs need to access different types of resources, such as CPU, memory, other FPGAs, GPU, and SSD. This figure shows an FPGA board currently deployed in Microsoft data center to accelerate AI applications. In the center is a FPGA chip to implement user logic. This FPGA board is equipped with multiple physical interfaces for different types of resource access. The onboard DDR4 is for memory-intensive applications. The PCIe Gen 3 port lets FPGA to access CPU, main memory, and other devices in the host server. With the QSFP port, FPGA is connected to the data center network. Although application developers can customize any logic in the FPGA, the communication logic is highly reusable. Thus, FPGA vendors usually provide IP cores for each physical interfaces. These IP cores are highly related to the physical interface and change generation by generation. Above the physical layer, data center operators like Microsoft and Amazon provide their own data link layer stacks to hide the difference between each IP cores and to implement the data link layer protocols. Transport layer protocol like DCQC has been implemented in specific data center link layer stack, such as LTL. However, compared with the famous Internet hourglass architectures, the most important layer is missing. This restricts the FPGA to directly access all data center resources. In the next few slides, I will show the existing problems of current FPGA communication architecture. The first problem is about the interface. Although stack developers abstract the communication protocols, the interface is still quite different between each stacks. These numbers show the lines of code we developed to use each stack's interface. Note that using these wires are not as easy as calling a software API. Each line of hardware description language requires at least 10 times more effort to develop compared with using software languages. It usually takes weeks for development, verification, and performance tuning. The complicated interface make FPGA programmers hard to develop and hard to port between platforms. The second problem is that many resources are not directly reachable by FPGA application. Most of the resources like DRAM, SSD, and the GPU are only named in the server's local naming space, which makes it difficult for remote FPGA to use. For example, in FPGA accelerated large-scale big data analytics, CPU is involved to coordinate the data transmission, which limits the performance gain. The third problem is quite FPGA-specific. For FPGA applications sharing a communication stack, they are actually multiplexed in the stack's circuits. Programmer needs to implement a multiplexer and demultiplexer to handle the sharing. Since the stack interface is different, no general solution exists. For each case, developer needs to write a specialized one. These problems become very serious when two developers want to share a stack. They need to collaboratively write a multiplexer to handle this. And the multiplexing problem also exists between stacks. Currently, there is no general physical interface multiplexing scheme, and for current FPGA applications to simultaneously access local host DRAM and the local SSD without modifying the underlying stacks. Another problem is about security. Since FPGAs are attached to the server by PCIe bus, FPGA applications can easily access CPU, main memory, and other devices through the DMA stack, which makes it free to control the server. On the other hand, attackers from the outside can easily attack an FPGA application by injecting malicious messages. Here we conclude the existing problems as complex programming interface, separate naming space, no general multiplexing, and a security issue. To address these problems, we propose DUA. I first use an example to show how DUA works. In this example, application 1 wants to send a message to application 2 on a remote server's FPGA. It first sends the message to DUA on FPGA 2. DUA system finds that this FPGA board doesn't have an Ethernet port. It will forward this message to FPGA 1 in the same server through PCIe. And then DUA will forward this message to FPGA 3 through Ethernet. Finally, it can reach the destination application. From that example, we can see that DUA is an IP layer for FPGAs to access all resources in data center. DUA connects stacks and applications as a router and builds an abstract overlay network to unify all access. DUA leverages existing communication stacks and adopt new ones. DUA doesn't break the data center network, but leverages existing addressing and routing design. This makes DUA simple and easy to deploy. DUA has these key features. First, DUA enables every application to access any resource in data center directly. No proxy application is needed. Besides that, all the routing totally bypass CPU, which provides extremely low latency. DUA provides a unified BSC socket-like interface for all FPGA applications to access heterogeneous endpoint in data center, which significantly reduce the programming effort. Communication stacks development can also benefit from the unified interface. The third feature is DUA provides general multiplexing for applications and communication stacks. Programmers need not to care about implementing multiplexer anymore. The last feature is DUA protects FPGA applications and stacks from outside malicious traffic, and it also can protect the hosting server and even the data center network from anomalous FPGA applications and stacks. This block diagram shows the DUA system architecture. Since FPGAs are not suitable for implementing the complicated control logic, the data plane and the control plane is separate in DUA. DUA data plane lies in all FPGAs as a router. It provides efficient routing, unified interface, general multiplexing, and security. DUA puts the main control logic in the CPU. FPGA control agents only monitor and update the local status. Each server has a CPU control agent to determine all the control logic within this server. Well, for the data center-wide, DUA control plane is organized in a distributed way. Each CPU only maintains its local resource and routing information. In order to realize this idea, DUA uses a hierarchical address format. It leverages the server IP address as the first level and let each CPU control agent manages its local address at second level. For routing calculation, the idea is similar. Each server only manages its local routing. For cross-server communications, both sides CPU control agent calculates the intra-server routing path, and leverage data center routing paths to build the end-to-end route. By this design, DUA totally avoids global synchronization. DUA data plane consists of 3 parts. The overlay connects all applications and stacks with a unified interface and provides routing among all connected endpoints. This design also solves the stack multiplexing problem. DUA leverages all existing or can adopt new future stacks, and the DUA underlay solves the physical interface multiplexing and provides security check. Let's go deeper into the DUA overlay. In the center is a crossbar switch that switch message between stacks and applications. All routing tables are cached in the data plane to ensure all data transmission totally bypass CPU. To avoid the contention during table lookup, we let each connector keep its own routing table. Since only the active connections related to a connector need to be cached, the total table set can be very small. Since existing communication stacks all have their own interface, DUA as stack translator to convert between interfaces. Translators are carefully implemented to provide line rate and near zero delay. Here we use an experiment to show DUA's efficiency. We connect 2 FPGAs located in different servers by DUA. Both FPGAs do not have an Ethernet port, and the DUA will route traffic through PCIe to other FPGA with Ethernet support to make the end-to-end connection. The entire round trip passes PCIe for 4 times, Ethernet twice, and DUA for 4 times. The round trip time breakdown is shown in the bottom figure. DUA only introduces less than 200 nanoseconds latency, which is less than 5% of the total latency. And for each forwarding, DUA only causes less than 50 nanoseconds latency. Providing such low latency, DUA only introduces low FPGA logic overhead in our middle-end FPGA. A typical 4-port DUA implementation only consumes about 10% of FPGA logic resources. These numbers will be significantly reduced by 2 or 3 times on the next generation FPGA. And we use DUA to accelerate 2 typical applications. The first one is deep crossing. Deep crossing is a deep neural network proposed for handling web-scale application and datasets. The model trained from the learning process is deployed in Peng. The critical metric is latency, since it impacts the service response time. By using DUA, we easily extend the application from a single FPGA board to 2 FPGA boards and double the parallel degree of computation. It only uses 26 extra lines of OpenCL code to call the DUA interface to connect the 2 FPGA boards. The results show that 50% of latency is reduced by extend the application to 2 boards, which can greatly improve user experience. Another application accelerated by DUA is regular expression matching. Regular expression matching is widely used in application gateway and IDS inside data center. We use FPGA to accelerate the matching compilation by several magnitudes. However, current acceleration implementation need to use CPU to move data between FPGAs. With DUA support, we only need to modify several tens of lines of code to make data directly move between FPGAs. We further reduce the latency by half and improve the throughput up to 3 times. To conclude this talk, current FPGA communication architecture does not provide universal access to resources for FPGA in data center. We provide DUA as the IP layer of FPGA communication, which provide efficient routing, unified interface, general multiplexing, and security. We will open source this project soon. Thank you. I'm very happy to take any questions.
Questions for Ran? Let me start off. Do you provide a naming service for the FPGA to have access resources?
Yeah.
I see.
And this naming services like the IP protocol.
Any questions?
No, Silberman, University of Cambridge. So you said that your latency is about 150 nanoseconds to the device. Does that include any interfaces, and what is the clock frequency that you're using for that?
300.
And does that include any external interface also, or not? Is it entirely the pipeline?
Sorry, I didn't got.
Is that entirely the pipeline, or does it include also any external interfaces like serial links to the next?
Not include all the interface, just the routing time.
Thank you.
Any more questions? All right, let's thank Ran.